What's happening, y'all? So for this next focus notes video, you're going to be learning about exponential graphs and some logs as well. But just a quick joke for you. So this is called an expo marker, and I figured out why. Because it wears out exponentially. Anyways, so the graph for an exponential function, remember, looks like this if it's an exponential growth function, where your horizontal asymptote is the x-axis, and it hits the y-axis at this point 0, 1. So remember, any function, let's say y equals e to the power of x, when x is 0, it's always going to be 1 because anything to the power of 0 is equal to 1. So y of 0, if I want to call it that, is 1. So remember that one. Now, remember with exponential functions, if I change this e to the x to a negative, so that kind of changes the way that it's growing. Instead of growing like you see here, it's going to decay like you see here. But remember, when I plug in 0 to this function, I get e to the negative 0. Well, guess what? That's the same thing as 0. So e to the power of 0 is equal to 1. So my coordinate point, or my y-intercept, is still the coordinate point 0, 1. But instead of growing, it is decaying exponentially, just like this expo marker. All of my expo markers run out so quickly, so that's why it's called expo in my view. Before I move on from exponential functions, I wanted to explain what this negative x. So remember, we can also write this as y equals, instead of e to the negative x, we can write this as 1 over e to the positive x. These two are the same thing. So whenever you see a negative exponent, it's kind of like it's a fraction, where the exponent should be on the bottom if you're writing it as a fraction. But when you bring it to the top, it becomes negative. Alright, so let's move on to exponential operations, or properties, whatever you want to call them, laws of exponents if you want to call it that. So remember, when you're multiplying any two numbers that have the same base, if you're multiplying them, then you can add their exponents. So x squared times x to the 5th becomes x to the 7th. If you're dividing, you can subtract the exponents if the bases are the same. So 3 minus an invisible 1 here would give you x to the 2nd power. If you're taking a power and raising it to another power, so if I'm taking x cubed raised to the 4th power, here I multiply, so it would be x to the 3rd raised to the 4th power would be x to the 12th power. Remember, 1 over x, this is the reciprocal one. We can handle this, like I showed you previously with the e to the 1 over e to the x. It's the same thing as changing the exponent here from positive to negative if I'm bringing it to the top. So there's going to be a lot of times when we want to do that. So since the exponent here is positive 1, it would be negative 1 at the top. If it was x to the 4th power, then it would be 1 over x to the 4th power would become x to the negative 4th power. And then finally, when I have a fraction, remember, I can write this as a radical. We often do that. We often see it like this, but we'll have to convert it to radical form. So remember, the number on the bottom tells you what the root is. So if it's over 2, it would be square root. Since it's over 3, it is cube root. And then the number on the top tells you what the exponent is. So it would be x to the 2nd power. So just real quick to reiterate that one, if I change this to 5 over 7, then the bottom number tells me the root, so 7 would be outside, and then the top number tells me the exponent, so 5 would be inside. If you want to talk about it like, or think about it like top in, bottom out, top goes in, bottom goes out. So again, just to point out my joke again, exponential means growing or decaying really fast. These are called expo because they go away, they run out of marker very fast. So, yeah, proud of that one. Anyways, so exponential and log, so the relationship between them is that they are inverses. So algebraically, it would kind of look like this. If y equals log of x base a, then a to the power of y equals x. So this would be written in log form, this would be written in exponential form. So, just to kind of nail that property home, I'm going to switch this y equals 2 over here. So I'm going to move it over. And then I'm going to remind y'all how we got from log to exponential form. It's just the snail method, or the arrow method. So we start with this as my base for my exponential and my log. We raise it to the power of this, and then equal it to this. That's how I get a to the power of y equals x. So that is a key relationship between those two. Now, since they are inverses, exponential and log, that means if I have a coordinate point in exponential, let's say I have an exponential point x comma y, and if I want to figure out what the log version of that is, then I would switch those two, so it would be y comma x. So we'll see that on the graph in just a bit. But that's what the inverse relationship is between the two functions, exponential and log. Alright, so we just talked about the exponential graph before this, and we realized that, remember, it grows and it crosses the x-axis with the y-axis at the point 0, 1. So remember, since these two are exponential functions, it would be a reflection, the log graph would be a reflection of this along the line y equals x. So the log graph would be a reflection doing something like that. So hopefully you can see the inverse relationship between the two. And since the exponential function crosses the y-axis at 0, 1, that inverted point would be the point 1, 0. And instead of crossing the y-axis there, it crosses the x-axis here. So remember, that's the relationship between these two functions. Exponential and log are inverses of each other. So remember that there are a couple ways you can choose to evaluate logs. One way is to rewrite it in its exponential form. So if I want to figure out the log of 64 base 2, I can set this equal to a variable, let's say x, and I can rewrite it in exponential form to help me solve that a little bit quicker if I don't know. So remember, using the previous method, the snail method, I'm going to take 2, raise it to the power of this, which I'm trying to figure out, and equal it to 64. So 2 to the power of x equals 64. So this becomes the equation that I would then solve. And again, you can solve this multiple ways. You can think 2 to the power of what equals 64. You can just count them. So 2 to the power of 1 is 2. That's not it. 2 squared is 4. 2 cubed is 8. 2 to the 4th power is 16. 2 to the 5th power is 32. So 2 to the 6th power gives me 64. So x must equal 2. I'm sorry, 6. Why did I write that? 6. X must equal 6 because, again, 2 to the first is 4, so on. So 2 to the first is 2, 2 to the fourth, to the second is 4, 8, 16, 32, and 64, what we're looking for. So 2 to the power of 6 is my answer, or 6 is really what that equals. So I can then go around and erase all this stuff and say the log of 64 without using a calculator is equal to 6. So the other way to solve this, to figure out what the answer or what a logarithm is to cancel out the bases. So cancel out a base of 5, because remember, exponentials and logs are inverses of each other. So I can think, how can I represent 125 with the base of 5? 5 to the power of what gives me 125? You can probably think of it in your head. 5 to the power of 1 is 5. 5 squared is 25. 5 cubed, hopefully you know that one now, is 125. So 5 to the 3rd power is my answer. 3 would be my answer. If that's too quick, you can always rewrite 125 as 5 to the power of 3. You can put that 3 on the inside or the outside of the parentheses. It really doesn't matter. But the point is, this 5 and this log base 5 are inverses of each other. They cancel each other out and leave you with the same answer that we got here. Alright, so now we're going to go ahead and solve logarithms. However we can. I'll show you 2 different methods. But before we do, I want to make sure, something I didn't cover yet, is what happens when we see log of x with a base of 10? Well, we won't see log of x with base of 10 because that's called the common logarithm. So instead of seeing a little 10 as your subscript, you're going to see this, where there is no number. So that is the common logarithm. That's one that we use a lot. So instead of writing a little 10 subscript there, we just put log of x. So remember that from last year. And then same thing with e, log of x base e. We don't see that. We see the natural log of x. So when there's a base of e, that means it is the natural log. So those are the 2 logs that you won't see a subscript for. So going back over here, I'm going to go ahead and erase this because we don't need this anymore. But just keep that in mind, that the log of x is the base of 10 and the natural log is the base of e. So to solve this, I'm going to show you using the inverse property first, and then I'll show you a different way in just a bit. But if I'm looking for log of 4x minus 7 base 3 equals 2, remember I'm solving for the x, which is inside of the parentheses. So I want to get rid of everything outside the parentheses first. So I want to get rid of this logarithm on the left side. how do I do that? I can think of inverses, right? But I can't divide by 3 because multiplication is not the inverse of, or division is not the inverse of logarithm. What is the inverse of a logarithm? It is an exponential base. So I would raise both sides with a base of 3. So I would say 3 to the power of all this, and 3 to the power of 2. So this is kind of like my side work that I'm doing in my head. I don't need to write this step down on my paper. But we can see that the 3 and the log base 3 are going to cancel each other out and leave me with what's inside here. So 4x minus 7. And over here, I'm left with 3, not times 2, but to the power of 2, because it was an exponential base that we used. So 3 to the second power is 9. And then it becomes a super basic algebraic problem. 4x equals 16, and then divide by 4. I'm not even going to write that step down. I want you guys to get to doing this step in your head. So divide by 4, 16 divided by 4 is 4. Okay? So the last thing you want to do is you want to make sure that this is a valid answer by plugging it back into your equation. Remember that we cannot take the logarithm of negative values, or 0, only positive numbers. So we can only, if we plug in a number and we get a positive, we're good. If we plug in a number and get 0 or a negative, then we're not good. So if I plug this into this equation, 4 times 4 is 16, minus 7 gives me 9, so that's a positive number. It's good. And if I were to check my work, I would still be right. So quickly here, I'm going to show you the second method. I told you I was going to do both. I prefer the first because you're going to use that more often. It's a more general strategy. But the second method is to take this and convert it to an exponential function. So you could take this and convert to exponential by doing the spiral thing, right? So you have 3, you're going to raise it to the power of 2 and equal it to this. So 3 to the second power and equal it to 4x minus 7. So then you could solve the equation like that. That's what we ended up with before, but again, this is more specific, a specific way to solve this type of problem, not necessarily a general way to solve all types of problems. Okay, so the last type of problem that I need you to worry about with logarithms is something that looks like this, where we're getting rid of that e before we do anything. So remember, this is where you need to start thinking, what is the inverse of e, or what is the inverse of logarithm to solve these? So e to the power of 2x plus 1 is what we're given. I'm solving for 2x plus 1, and that is inside of the exponent. So what do I have to do? I have to get rid of everything outside of the exponent. What do I see that's outside of the exponent? Just this e. If there was a multiplication or a addition subtraction outside of that, then I would get rid of that first. But since e is the only thing there, I want to go ahead and get rid of it. How do I do it? Do I divide by e? No, that is wrong, because dividing is not the inverse of raising something to a power with the base. So instead, I want to think of what is the inverse of an exponential base, and that answer is a logarithm with that same base. So I'm going to take a logarithm on both sides here to get rid of e, and I have to take a logarithm with the base of e. So or just going back to, remember the two bases that I had, if the log is a base of e, we don't write log base e, we write natural log. So I'm going to take the natural log of the left side, and then I'll also squeeze it in here. Remember, this is kind of like my notes, or like my scratch work, I should say. Let me just make some room here. You don't have to write this step out, but it helps to see how to get from one step to the other. So I squeezed in a little bit of space between the equal sign and the 10 to fit in a natural log to show you that I'm doing the same thing on both sides. So over here on the left, the natural log and the e cancel out and leave me with the exponent 2x plus 1. And then on the right, I want to ask myself, do I know the natural log of 10 without a calculator? I don't, so I'm going to rewrite it as natural log of 10. A lot of your answers will be in the form of a natural log, and that's okay. You can calculate them at the very end. Once you're done with all the algebra, you plug everything in at the same time. So then I just handle this like a normal problem. I would subtract 1 from both sides, so I'd get, 2x equals natural log of 9. Does that make sense? It shouldn't, because I am subtracting 1 from natural log of 10. So I would need to find this first and then subtract 1. So 10 stays there, and then I'm subtracting 1 from that. So that's how I would write it. So don't write natural log 9. I did that to throw you guys off. You're subtracting 1 from the entire natural log. And then finally, you're dividing by 2. So x would equal, if I split this up into two fractions, I could. Natural log of 10 divided by 2 minus 1/2. That could be my final answer. And no, you cannot simplify that 10 over 2 because, again, you're taking the natural log of 10, which is going to be a decimal, and then dividing by 2. It's not going to give you the same thing as natural log of 5. Alrighty guys, I hope you learned a lot from this video or reviewed a lot. Just remember to use this as you work on your assignment and consider joining the golf team. I need some boys golf players on my 8th period attendance roster, so please join. See you later.